let's sketch an energy level diagram. What was our energy again? E equals n squared h squared over 8m L squared. To make things simple, I'm just going to abbreviate that, and let's call that a letter. And let's use a Greek letter. So let's call that n squared alpha. Okay? So h is a constant, m is the mass of your particle, that's a constant, L is the length of your box, which you defined as a constant. So alpha is just a constant. So let's look at our allowed energy levels on an energy scale. What's the lowest allowed energy? When n equals 1. And so 1 squared alpha would be, so this is E sub n, 1 squared alpha would be alpha. So if this is 0, the lowest energy is alpha. This is your ground state. Okay? Your ground. Okay, this is your ground state. The lowest energy level. You'll notice it's not 0, right? This is what you call your 0-point energy, but it's not 0. Okay, and there's a reason why it's not 0. Because if energy would be 0, then for you to get an energy equal to 0, you'll have to use n equals 0. But n equals 0, we said earlier, was not acceptable because that would make the function, the wave function 0 everywhere. So that would make the particle not exist. Okay? All right, what's the next allowed energy level? N equals 2. So E2 would give you 2 squared times alpha. So that's going to be 4 alpha. So it's 1, 2, 3, 4. So the next allowed energy level is 4 alpha. What's our next allowed energy level? E3 would be 3 squared alpha, would be 9 alpha. And what would you have there? 4, 5, 6, 7, 8, 9. What's happening to the gaps between allowed energy levels as your n increases? It's getting bigger, right? Those are your allowed energies for your particle in the box. Now, here's the next question. What happens to the energy gap? It increases. In fact, you can show that it does increase by just saying, okay, adjacent levels. That means I need to know the difference between the energy between quantum state with n plus 1 minus the energy for the nth level, right? So that's the gap between allowed energy levels. So how would I derive that expression? I'm going to say that's n plus 1 squared h squared over ml squared. Let's just call that alpha to make things simple. Alpha minus n squared alpha, right? So that's going to give me, that's n squared plus 2n plus 1 alpha minus n squared alpha. So that gives you, n squared cancels out, so that just gives you 2n plus 1 alpha. Okay, so the gap between adjacent levels does increase as n increases. It's linearly dependent on n. Okay. All right. What would happen to the energy gap between adjacent levels as the length of the box becomes very large? What did we say delta E was? 2n plus 1 alpha, right? And what was our alpha? It's h squared over 8m L squared. What happens as L becomes large? Your delta E is going to approach 0. So the less you constrain your particle, this is generally what happens. The more you constrain your particle, you say you get more pronounced quantization. You have gaps between adjacent energy levels get bigger. But the less constrained the particle is, the bigger your L. That means your particle is less constrained, the less you see quantization. In other words, the gaps between adjacent energy levels get smaller. Now, what did we say? In classical mechanics, there is no restriction on the allowed energies, right? And so you are basically approaching what we would call the classical limit in this case when you're making your L very large. It essentially becomes a free particle. In a free particle, you have a continuum of allowed energy levels. Energy is no longer quantized.